Welcome to our discussion on rounding numbers. A lot of this is going to be vocabulary, a lot of it's going to seem kind of confusing, and a lot of it is actually kind of silly and not really necessary other than to help you get the answers right on homework and tests. But in real world situations, it really boils down to, can you round properly? That's really all that matters here. All right, let's look at some vocabulary. First, we talk about significant digits. You may have heard this before. Some of them make sense, some of them don't make sense until we actually look at some examples. So non-zero digits are always significant. That kind of makes sense. Zeros that follow a non-zero digit and lie to the right of the decimal point, as in 4.20 or 3.00, those are also always significant. And that might seem silly because you're like, what's the difference between 3.00 and just 3? Well, you'll see here in a second that there actually is a big difference, and that's why they're significant. Zeros between non-zero digits are also always significant. 4002 or 3.06. Those are obviously significant because without them, the first one would just be 42, which is a totally different number, right? And the second one would be 3.6, which is also a totally different number. So those are important. Okay, zeros to the left of the first non-zero digit, so 0.006. They're talking about the zeros after the decimal. Obviously the zero before the decimal is significant, but the ones in between aren't. And again, you go, how is that not significant? Because 0.6 is a different number. Well, it really all boils down to, if you list these numbers in scientific notation, it's, what's significant and what isn't, is kind of what it all boils down to. And if you don't understand what scientific notation is, we'll talk about that here soon. Okay, zeros to the right of the last non-zero digit, but before the decimal point. Not significant unless stated otherwise. And again, once we look at some examples, these will make more sense. So let's look at some examples. If we have a time of 11.9 or a length of this, a weight of that, blah, 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 let's figure out how many significant digits they have and what is implied by them. So we'll take the first two. 11.90 seconds has 4 significant digits, and the reason why the 0 is significant is it now implies the accuracy, right, of your measurement. You've measured it to the nearest 0.01 seconds. Without that 0, you're just assuming that you're rounding to, a tenth of a second instead of a hundredth of a second. So that's why it becomes significant. It tells you how accurate your rounding is. The next one, same idea, you only have 2 significant digits. The reason why all those zeros in front of the 67 aren't significant is because you can rewrite this in terms of micrometers or micrometers. It's the same thing as putting it in scientific notation. You can just list that 0.00067 meter as 67 micrometers, and now it's very clear that it only has 2 significant digits. Same thing with grams. 0.003 grams can be 3 milligrams, and that 0 after it implies that it actually rounded to 4 decimals in the first one. So then you would have 3.0 milligrams. And again, that 0 is significant because it gives you the level of rounding, how accurate this measurement was, how precise it was, how many decimal places did they go out. And then finally, 240,000 as a population only has 2 significant digits, and it implies that it's been rounded to the nearest 10,000. Now, you could argue that that's actually an accurate number. There was exactly 240,000 people, and therefore it's accurate all the way out to the ones, right? The single. But it's highly unlikely. It's most likely that that's been rounded, and then that's why you only have 2 significant digits. Again, like I said, some of these kind of feel kind of silly, but it also comes back to the idea that you could report it in scientific notation, as it is here, but when you put that 0 after it, that implies that that's the decimal you rounded to. You rounded to that place, and therefore you have 3 significant digits. Here's an example of rounding to a specific number of significant digits. So 7.7 times 9.92 with 2 significant digits, you end up getting 76.384, but to round to 2 significant two significant digits, you basically lose all the decimals and you just round to 76. Likewise, on the next one, if you round that to 4 significant digits, you get, well, a huge number, but if you do it in scientific notation, this is what you get here, 1.7, blah, blah, blah. And then rounding that, or listing it basically, with 4 significant digits means just 1.731 times 10 to the 10th, and you can see that it's been rounded. If you listed this out, it would be 1731 and then 7 zeros after it, and you see how all those 7 zeros at the end would be considered insignificant because we actually rounded. Right? That wasn't the actual number. The actual number was 1730544 and some zeros after it, but we rounded it up. So significant digits really kind of comes back to your level of accuracy, how you've rounded. All right, here's some vocabulary. Don't really care about it, but random error is just something that happens. Systematic errors are where the error is always in the same way. Like this would be a problem where your scale is off by 2 pounds. So everything that you weigh is going to come back 2 pounds too heavy because your scale is off by 2 pounds. That would be a systematic error. Random error is just unpredictable and they just happen and there's really not much we can do about them. The size of your errors, you have two things, and it's really very similar to what we'll see with other topics with percentages. You will always have absolute something and relative something. An absolute something, in this case an absolute error, is the actual distance between the two errors, right? So an absolute anything is the absolute actual distance between those two somethings. So when you talk about an absolute difference, let's say, it's the actual numerical difference between two numbers. But when you talk about a relative something, it's taking that actual distance, right? So that it's taking that absolute something and then dividing by a reference number. And the reference number is always your starting value. And if you don't have a starting value, then we call it a reference value, right? So you absolute error, the difference is between two things, which is the actual difference, right? The actual error. And then the relative error is that actual error divided by the true value. That becomes your reference value, right? So if we standardize, kind of generalize these things so that when we see this over and over and over again with other things, we'll see absolute something, relative something. Just realize that they're all the same. The absolute something is the actual numerical difference between those two things. And then the relative something is always that absolute amount divided by some reference number. Here's a simple example. Budget surplus of 17 billion turns out to be 25 billion. So the absolute error in your measurement is the difference between 25 billion and 17 billion, or 8 billion. And then the relative error is that absolute error of 8 billion divided by the true value. And the true value happened to be 17 billion, right? And so that's a 47.1%. Now, you might argue that the true value was what it actually turned out to be, and that's totally fine. These questions need to be more precise, right? I would have interpreted the true value to be the 25 because that's what it turned out to be. They interpreted the true value to be what you budgeted. So that, it's kind of like your guess. So in this case, they're saying how far off you were from your guess. In my case, if I ran it with my numbers, it would be how far off are we from what actually happened, okay? Accuracy describes how closely your measurement approximates a true value, right? So how far you deviate from the actual amount. And then precision just tells you basically the level of detail in your measurement, i.e. how many decimals out are you going to go, right? How precise are you with your measurements? Now, these rounding rules, don't waste brain power trying to memorize them. Other than a couple key questions, maybe on a homework or something, the bottom line is always round to as many decimals as you can, and then round to however many you're told to. But there's kind of an unwritten rule, if you're not told specifically what to do, that you round to the least precise number whenever you're adding or subtracting something. And then when you're multiplying, you round to the same number of significant digits as the measurement with the fewest significant digits. So you're basically rounding to the fewest number of significant digits for all numbers involved in the multiplication and division. So here are some examples. There was a book written in 85 that states the oldest Mayan ruins are 2,000 years old. How old are they now? Well, since the book was written in 1985, it's basically 30 years old now in 2015. So you might be tempted to add 30 years to 2,000 years to get an answer of 2030, but since the book states that the Mayan ruins are 2,000 years old, that sounds like rounding, right? 2,000 is a pretty round number. It's probably not exactly 2,000 years old. They rounded to 2,000. So really, it has a significant digit of only one, right? The 2 and the 3 zeros are insignificant. It's being rounded to the nearest 1,000 years. 30 is precise to 10 years. So we have to basically, again, round 2030 back to the nearest 1,000 years. So in this case, we would still say it's only 2,000 years old, despite the 30-year age of the book, because that first number was just so unprecise, right? It was rounded a lot. Here's another example. 82,000 people. They plan to spend $41.5 million this year, assuming the money must come from taxes. What average amount must the city collect from each resident? So basically, you're trying to figure out if you have $41.5 million and you spread it evenly over 82,000, roughly how much is coming from each person. Well, 41.5 million has 3 significant digits. 82,000 really only has 2 significant digits, again, because we're assuming it's rounded. It's very doubtful you're going to have exactly 82,000 people in your town. It's probably 82,000 and change, or 81,000, 800 and something, and it's rounded up. But basically, you've rounded somewhere to the thousands, right? So only 2 significant digits. So after you do the multiplication, so there's your 41.5 million with all of the zeros and commas. Divide that by the 82,000 people. Get your answer of 506.10, and now round that to 2 significant digits. Means you have to round up to $510 per person. So that's the rough, amount that each person pays. Okay, so those are the rules about rounding numbers and significant digits. The bottom line is don't round intermediate steps. So if you're going to do multiple steps to get your answer, don't round until the very end. If you have to round intermediate steps because you just don't have the ability to carry a lot of decimals, then the rule of thumb is always round intermediate steps a lot less, right? So with more decimals than your final answer. So if you know your final answer is going to have 2 significant digits or 3 significant digits, if you have to round those intermediate steps, then round them to like 6 or more. Kind of double or even triple the amount of significant digits. And then above and beyond that, just round wherever you're told to round.